Alright, so we discussed how to find eigenvectors when you have complex eigenvalues, but we really didn't discuss when we have a system of differential equation and complex eigenvalues, how do we write down the general solution, right? So now we are only dealing with 2 by 2 systems. That means how many solutions you can expect in the fundamental set of solutions? 2, right? x1 and x2. Now, if you can find the x1 and x2 in this complex case, you can take the linear combination. So it's not a mess like the repeated eigenvalue case, okay? So it's good, right? So we can just take the linear combination, just like in distinct eigenvalue case, and write the solution. But getting that x1 and x2 is a little bit complicated. Now, we have formulas for x1 and x2. Look at these two formulas. So what you do really is, you get the complex eigenvalue, you get this eigenvector corresponding to that complex eigenvalue, and you know this eigenvector is also complex. So you use this information from this eigenvalue and eigenvector and construct this x1 and x2. Now look at x1 for example. What do you see in x1? You see alpha, right? And you see beta. And you see b1 and you see b2. Do you know these things? Well, you know. So what is alpha and beta? What is alpha? Alpha is the real part of the eigenvalue, right? What is beta? Beta is the imaginary part of the eigenvalue. So when you find the eigenvalue, you automatically get alpha and beta, right? Good. Now, what is capital B1? Capital B1 is the real part of the eigenvector. What is B2? Imaginary part of the eigenvector. So they are like the analog of alpha and beta in vector sense, right? So b1 and b2 will be vectors, but they are coming from the eigenvector. So when you find the corresponding eigenvector k1, you automatically get b1 and b2. Now see, the way you write the first solution is b1 times cosine beta t minus b2 times sine beta t times e to the alpha t. And the second solution is b2 times cosine beta t plus b1 times sine beta t, everything multiplied by e to the alpha t. So if you know alpha, beta, b1, b2, you are good, right? Now here's the thing. I will do an example in this video also, okay? But really then you might ask the question, well, it seems to be like super simple, right? Because you only need a one eigenvalue. You only need a one eigenvector. Lot of workload saved. And really, do I need to memorize these two formulas? Well, that's a question for your instructor, okay? Before the exam, you should check with your instructor and you should ask from her or him that whether they will give the formulas in the exam or do you have to memorize the formula, okay? All right, so let's move on. Let's do an example. So in the note, in the example 1 in the note, okay, I'm not going to go through the workload of finding eigenvalues and eigenvectors in this video, okay, for this specific example. Let's say you got your eigenvalue to be 1 plus I, just the one eigenvalue. You know the other eigenvalue is 1 minus I, okay, and let's say the eigenvector corresponding to that is I1. Okay, now you found the eigenvalue, you find the eigenvector. You know how to do that now, right? Now what you need to do is figure out alpha and beta and b1 and b2. So what is alpha and beta? Alpha is 1 here, beta is 1, right? Always remember, beta is independent of sign. Beta does not have a sign, but alpha can have a sign, okay? All right, now what is b1 and b2? So let's rewrite this complex eigenvector in like a complex number. So we can decompose this as the real part is 0, 1 plus the imaginary part is I1, 0. Right? So we learned that how to do. So what is b1? b1 is the real part, which is 0, 1 vector. b2 is the imaginary part, which is 1, 0. Don't include I to b2. b2 does not contain I. That's something that you should remember or you should write down. Keep that in your mind, okay? b2 is again acts like beta. Beta, does it come with I? No, it's just the coefficient of I. Here, in the eigenvector, b2 is like the coefficient vector of I, okay? All right, so now you know all this information. Let's write down x1. So what is x1? b1 times, b1 is 0, 1, times cosine beta t, so beta is 1, so it's cosine t, minus b2 is 1, 0, sine beta t is just sine t, e to the alpha is 1, so e to the t. Now x2 is really b2 is 1, 0, cosine t, plus b1 is 0, 1, sine t, e to the t. So you just use those formulas and write down the two solutions, two linearly independent solutions. Now, before I write down the general solution, I would like to simplify this. Okay? Alright, so it's not necessary to simplify it, but it's good to see. It's good to simplify it, especially if you get an initial value problem. So let me do that here, okay? So x1 can be written. Now see, you can multiply this vector and cosine t. So what you get is 0 times cosine t is 0, 1 times cosine t is cosine t. So that is what you got from the first expression. Minus here 1 times sine t is sine t, 0 times sine t is 0, and e to the t. So what is this? So if you subtract, what do you get for x1? So what you get is 0 minus sine t is minus sine t. You subtract element by element. Cosine t minus 0 is cosine t. And this is times e to the t, right? So that is the simpler version of x1. Now can we do that for x2 also? Yes, we can. So here we get cosine t 0 plus 0 here sine t. Right, so if I distribute that cosine and sine among relevant vectors times e to the t, so we can add these two and write cosine t plus 0 is cosine t, 0 plus sine t is sine t, times e to the t. So that's the simpler version of x2. Now we can use these simpler versions of x1 and x2 and rewrite the general solution. So x is c1, x2 is negative sine t cosine t e to the t plus c2 here cosine t sine t e to the t. So this is the general solution for the differential equation. So that is how you write it. But if you decide to write if you decide not to simplify, just like I did, like c1 times this longer expression plus c2 times this longer expression, that's also valid, right? That's also correct. You can leave it like that also, no problem. So this is how you write a solution when you have complex eigenvalues and complex eigenvectors. Okay. All right. Thank you very much.